Okay, so we've talked, let me get into here real quick. Let's see. Hold on a minute. Let me stop that recording. Okay, now we're ready. All right, so we talked about trust and trust analysis. And we looked at behavior last week, and we looked at method of joints. So today we're primarily focusing on that method of sections. So we already understand this, but you guys hopefully now realize that trusses are and frames are usually used in really large structures. And hopefully if you've been driving around watching construction going on or over bridges or stuff, you can start to see these trusses in actually real form. So we talked about breaking them down into smaller free bodies to determine forces. And that's what we've been doing in joints. We're going to do a similar process here. And we made some distinctions between trusses and frames. We talked about that last week. That the truss we define as a pin-connected structure. So remember, that's just the way we model it to simplify it. So that then puts our members in pure axial tension or pure axial compression. And remember, as loads would change across that truss, a member that is in tension will have the tendency to go to compression and vice versa. So between the two states, you actually can have zero force running through that member, as we saw in a couple of those problems. And a frame is a pin-connected structure also, as we model it. They're two-force members, but we also have bending to deal with. So it does make it a much more complicated thing. And we use a different process entirely to analyze it. But remember, we're going to skip the frame section in chapter 4, so we will not be responsible for that. So again, this is what we're looking at. We talked about this quite a bit last week. When we have a member in tension, this is where it gets the term two-force member, and it's axial because this line of action is running basically right through the center line of the member itself. So when it's in tension, you can see the forces are acting that way, and in compression that way. So we're going to have the same process as we get into method of sections. So we always talk about a truss being a framework of triangles, essentially. And we define them laying all on the same plane, but that's not always true. You know, a three-dimensional truss or a large bridge that you go over, such as the Brent's fence, that's nothing but a bunch of triangles, but that's all three-dimensional. Okay, so that triangle yields that very stable shape. We talked about that last week. Okay, and we talked about this as well. So let's get into the stuff. All right, truss terminology. Again, that probably bears repeating a little bit. We talk about span and panel, height, lower chord, upper chord, joints and web members. So that little diagram is really good. Remember, that is not in your book. And we've been working with that quite a bit. Basically, we don't make a distinction of whether that's a lower chord. I mean, we just all call these web members. So what we're solving with joints, we're just solving all the member forces through here. And we're essentially, well, technically what you're doing is solving joint forces, but we're going to essentially be doing the same thing with the method of sections today. So we'll use that kind of concept. Okay, so these assumptions we made for trusses, let's go back through that real quick. That bears a review as well. So we always consider them members connected by frictionless pins. Frictionless means you do no bending, so those things are free to wobble back and forth. Older trusses actually were pinned, and we had some catastrophic failures due to that, because if either the member failed or the pin failed, basically the whole thing came down. And there was a really famous bridge it's just up the Ohio River by Gallup Police called the Silver Bridge, which failed. And when it failed catastrophically, and it was an eye-bar that failed, and the whole thing just came down. It was like loaded with cars too. So that was just right on the Ohio River up by Gallipolis. But the newer ones, the modern trusses, they're bolted or welded, or sometimes they use rivets, but I think primarily they weld them nowadays. And they will use what's called a gusset plate where they connect in. Okay, all members lie in the same plane. That keeps it two-dimensional for us. All forces on the truss are applied at the joints, and then the joints push on or pull on the members. And so that ensures a bending associated with the truss is not directly attributable to the load. We also have stated last time that the self-weight of each member is negligible, or we just ignore it. So what you're doing is you're applying it through the concentrated loads themselves. Okay, we know that those members are extremely heavy, but the way that structural engineers look at it, they put it into the actual weighting of the concentrated loads. And so all members then are subjected to two-force kind of thing, either tension or compression. Okay, so we talked about this, member forces and joint forces. Okay, and they have to be in equilibrium. So notice if your joint, you've got a force 1 coming this way and this way, that's more or less pushing on that, but this is pushing back. So when you add these two together, they cancel. When you add those two together, they cancel. So that's how we get equilibrium. Okay, so let's get to the new stuff. So method of joints, we know, once we have our reactions, it allows us to start at a joint and analyze the forces at that joint. Then we go to the next joint, and we just keep doing that process until we get to the end where everything will go back to 0. And what sections does, it's an alternate method that allows us to analyze selected member forces by taking a section cut through the members where you wish to find forces. Now, you can't do typically just one section cut. You may end up having to do several section cuts if you want members that are not in the same section where you're cutting. But once you do your cut, you're going to apply equations of equilibrium. And at this point, you now no longer have a concurrent force system. You're going to wind up typically with a non-concurrent force system. So if it's truly non-concurrent, then you can utilize or apply sum of forces in X equals 0, sum of forces of Y equals 0, and sum of moments. Now, moments are the tricky part, but they're also the part that gives you a lot of times the solution. So you want to be smart with moments, and that's where you can take lines of action and follow them into a concurrent point and take your moment there. So you'll see what we get at, what I'm talking about as we get into this process here. So the moments are probably where you take the moment selectively is very tricky, and not necessarily tricky, but you got to be smart how you do it. So you kind of got to watch that. So here's an example, and there's a better picture of this shown on your handouts. But what we see here is in this process, we have the complete truss here, notice, okay? And you have a reaction over here. This is a pin, so you have two reactions, and you have a roller over here. So we're looking to solve the section here, that member, it's like BD, and then, or BC maybe, can't read this. And then you want to set this member and you want to do this member. So we literally just take a cut right through here and slice it. And we can either look at this side of the section or we can look at this side of the section. So notice what you do is you've got a free body diagram down here, which is the left side of that section cut. So when you do this, what you're doing is you're bringing in everything that's on that section. So notice this force here, that one, the roller or the pin comes in, and these are the guys that you're actually solving. So all these web members here, that lower chord, they never get solved. It's just what's happening right there, that member, and that member. And the same thing is true for the right side. So we could do the right side as opposed to the left side. But again, what's really critical about this, when you draw the free body diagram, you have to make sure you include all of the forces that exist within that section, but nothing else. So notice I have two external loads up here. The two external loads come down here in this section cut, the reaction, that reaction right there, and then we're left with just these guys right here. It's the same ones that we're solving. Okay, this one's a little bit more complex because we've got more forces. This one's basically, we're going to get the same answers, but by doing it over here, we have a little bit less work. Okay, so you're usually going to be directed on what section you're going to cut to. You don't have a choice. If you're a structural engineer, you probably do, because they're going to be looking for selected aspects. The one thing too about this, whatever you feed into this, you're going to get an answer. But if a reaction's wrong, you'll never know it. So unlike method of sections, or joints rather, where we know when we're done whether we're correct because we know everything has to resolve to zero, with a section you'll never know that, because if one or both of these is incorrect, you're going to get answers here, but it's not going to be right. So that's the dangerous thing about using sections. And the other thing about sections, you don't get every member. So I don't know any of these here internally. All I know is where I did my section cut. Okay. All right. So the procedure for method of sections, it's a pretty easy step process. So the first thing, of course, is to solve your external support reactions. And this is all important in this. You cannot blow external support reactions. If you do, the whole problem's gone. Your history with it. Okay. But what this will do is give you additional forces that will aid you in solving it through equilibrium. Okay. So that's no different than the method of joints, except joints, we do have that resolution at the end. Sections, we don't. So this step right here is key to everything. Okay. Then you section the truss through the members that are to be found. So you simply draw basically a cut through it, and then you're going to draw a free body diagram based on that. So here's the key things to remember with your section. Remember to cut the truss completely in two, so that you have basically two sections you could draw. And where you're doing the cut, you're generating unknown forces through those sections. Okay, so several cuts may need to be solved, but to require all of the unknowns. So it's not unusual to maybe do one or two sections on a problem. And the good news is you've already solved the reactions, so you just keep using that information. So it's not like you have to reinvent that every time. Okay. So you work with only the piece of the truss, work with only a piece of the truss as a free body diagram. So what that's saying is when you create the free body diagram on that, you don't work on both free body diagrams like that. We had the left side and we had the right side. We just do the one side. Choose the one, in my opinion, that has the least amount of forces, because then it just makes less work. You don't have to worry about as many forces in X, Y, and moment. Okay. But you have to make sure, and this is critical, you add all the external loads and reactions that occur on that section. Some people will try to add other forces, or they delete them. If you do that, of course, you're screwing it up too. And the only thing you're solving are joint forces that occur at the cuts. Okay. Once you have completed that aspect, you're going to write and solve your appropriate equilibrium equations. So you'll have one equation of sum of forces in X equals Y, one equation for sum of forces of Y, and you can do multiple moments. Okay, so you have one X equation, one Y equation, but you can do moments several different locations. And what I'm going to show you, I like to do moments more than one spot, because sometimes that gives me a little check on my own math internally. But remember, it's not going to save me. If I've blown my reactions, I've blown everything. Okay, so I can't stress that enough. So we're going to take a look at an example. Okay, and let me get out of here, and we're going to go to my whiteboard. Okay, so I'm going to do a problem, and we're going to do a section cut through this thing. So give me a minute to draw this. And I'll be right with you. Okay, so the first thing I'm going to do is let me draw my truss. Takes me a while, sorry about that. There's a lot of work in this, so give me a sec. Very good as it. Okay, so there's my truss. Now let me put some loads on here. So we got this thing loaded on the top. So the top chord has 3/4 and the bottom chord's going to have 3/4. I could have done that when I was there. So we got a load here, a load here, a load here, here. Okay, so we have 6 kips, 6 kips, 6 kips, and we have 6 kips, 3 kips, and 12 kips. Okay, so this thing's heavily loaded. We've got 8-foot panels here, so I'm going to put that symbol that represents or references the fact that those are all the same. Okay, and then we have 6 feet from top to bottom. Let me get that drawn up. So 6 feet here to here. Okay, everybody get the idea?
Yeah.
Okay, so let's put some reactions in here. Okay, so we're going to say that we have a roller on the right side and a pin on the left. So we're going to model this. Oops. I'm going to model that here. My pin's over here. Okay, so we have reaction, which is unknown at this point, and reaction. So this is H, so this is going to be reaction HV. This is going to be reaction AV, and this is going to be reaction AH, okay? So this is joint B up here, and then we have D, and then we have F. And we're going to have C, E, and G. Okay, does everybody understand my truss?
Yeah, I got it.
Okay, so ultimately what we're going to be after is solving the members right here. So we're going to want BD, CD, and CE. So you can see that truss is a mess, right? A lot of work. If you had to do this with joints, you'd be there for a while. What we're going to see with sections, we'll be able to get those members real quick. But the first thing we have to do is what? We have to solve the reactions, right? So this is a good problem for reactions. So let's go ahead and solve the reactions. So what would we do first? Sum of forces in X. I'm going to go ahead and solve X. What do we have going on in X? RAH. What do we know about RAH? Is there anything resisting it or pushing against it?
Is that just equal to 0?
Yeah, looks like all of our forces are vertical, right? So this one goes to 0, okay? So now that's important too. We need to know that, right? So we're going to now do a sum of forces in Y, okay? So in Y we have RAV plus RHV minus 6, minus 6, minus 6. That takes care of the top. And then we have minus 6, minus 3, minus 12. And all of that should be 0. Did everybody agree with that? You guys check me, and I'll get my number. So I get 39 when I add these up. You guys verify that for me. Somebody let me know if that looks right. So what I get is 39. Okay. So that gives us RAV plus RAH is equal to a positive 39, correct? So we now have to do a moment, okay? So our moment's going to be kind of messy. It's a long one. So let's, we can simplify that if we, oops, let me undo that. Oh, no, very good summation. Okay. So I'm going to take moments where I'm going to say clockwise is positive. Okay, so any suggestions on where we take moments? Now this will be really important when we get to the sections. So what about moment here? Pretty cut and dried, right? Where's your best place to take a moment?
A.
A or B, yeah, or A or H, excuse me. I'm so used to the B on the other side. Yeah, so A or H. So let's go ahead and do A. That's going to knock out 2 unknowns. But this is going to be messy because we got this. You know, you can combine these things, by the way. I could take, if I take the moment here, since these are on the same line of action, I could say 8 times 12, right? Instead of doing 8 times 6 plus 8 times 6. Does everybody see what I'm doing? Or not?
Yeah.
Okay. So you okay if I do that or not?
Yeah, it makes sense.
Okay. It just simplifies it. Instead of having 1, 2, 3, 4, 5, 6 pieces, you're going to get 3. Okay. Because these distances are the same to the same line of action, you know, algebraically, it works out the same way. So I'm going to say these two guys combined is 12. They're going in the same direction. So that's turning that thing clockwise. So we're going to say that that guy is plus 8 times 12. If you guys look back at this later on the recording, remember what we did there. We combined them. So what would be the combination of these two guys added together?
9.
Yeah, so and then the distance would be to that line of action is going to be 16. Also tending to turn it clockwise, correct? So that will give us a plus a 16 times 9. Okay, so we're just trying to work smart, make it simpler. Now that doesn't, you don't always want to do that, but since this one's so straightforward, I think it just works well. Okay, so if we add 6 and 12, since they're on the same line of action, what do we have?
24 times 18.
Yes, right. So we're going to have 24. So the distance over is 888. That's going to be a plus rotation, right? 24 times 18. Okay. Rotation, distance, forces, rotation, distance, force, rotation, distance, force. So then on the last one, that's going to be a negative rotation. And that gives us, we are 32 feet over. So we're 32 feet at RHV. All of that's equal to 0. So let's see what we solve here on our resolution. You guys check my numbers. Because like we said, if we blow this, we've blown the whole thing. And the reality is on this process, you'll get answers, but you'll never know whether they're right. You guys check this. I'm going to check this again. It looks like I got 672. Comes over as a negative 672.
Yeah, I got that.
Is that you agree? Okay, good.
Yeah.
All right, so 672 negative divided by a 32 negative is going to give me a positive number. $21 kips acting up. So we get 21 kips. Those aren't kips, I didn't mention that, but 21 kips acting up, correct? So when we plug that back into here, we get RAV is equal to 39. 21 comes in, comes over as a negative 21. So that gives us what? 28, 18 rather? 18 kips acting up. Okay. So again, if we make any kind of mistake here at this point, we're done. Okay. The section problem will still work, but yeah, you'll have a problem. Okay. So now what we're going to do, we didn't have to correct the sign on the direction on that, but we do want to go replace that information because that's more information. And over here, we know that that is 0 and the other one is 18. Also, I mentioned this before, you got to make sure that you get the right number with the right reaction. So it would be easy to put 21 over here and 18 over here if you're not careful, right? So you got to watch that. Okay. So there's our truss with the proper solution on that. Everybody okay with that? We all good?
Like where it says 8 foot, obviously I know that's 8 foot between each section there, but what's that thing that kind of looks like an 11?
This,
Yeah.
that's called a ditto mark. So it just
Okay.
means it's common. It's the same thing. Okay.
Okay.
Do you want me to put an 8 in there?
No, it's fine. I
Okay.
know it was 8, but I just didn't know what that mark.
Yeah. All I'm saying is ditto, ditto, ditto. So I'm just saying this is 8, 8, 8, 8. So another way of stating that, Jacob, would be to say that you have 4 panels that 8 feet. Okay. So this could be a panel, 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 panel. So when you're saying 4 feet or 4 panels at 8 feet, you're saying they're all the same, they're all common. But that wouldn't be true in all trusses. So you could have like 8 feet, 10 feet, 10 feet, and then 8 feet. So it just depends on the truss design, okay?
Yep.
Yeah, good question. I'm glad I just kind of assumed everybody knew what I meant, but that's good, okay? Perfect. All right, anything else before we get into the section cut? This was just stuff, this is chapter 3, right? At this point, nothing new, correct?
Right.
Okay, so here's what we're ultimately after. We want to know member the force and the quality, tension or compression in member BD. We want to do CD and we want to do CE, okay? So if we look over here, here's BD, here's CD, and here's CE, okay? So this allows us to simply take a section cut right through that and then bring in the forces that we need and resolve it based on this concept of method of joints, or method of sections rather, excuse me. I'm going to be saying that all day, okay? So what we're going to do is model a free body diagram now, and we have a choice. We can either go on this side of the truss and do the model, or we can go on this side of the truss. It doesn't make any difference, literally. It just means you may have more forces in one side than the other. So do you guys have a preference on which side that we model? Left side of the cut or the right side of the cut?
Wouldn't it make more sense to do the left side because there's less to do?
Absolutely, yeah. So if I literally just blow all of this stuff away, just erase it, or literally I'm doing this with a section cut. I'm just taking that and I'm doing that, okay? And what's left there is your section, okay? That's all you're doing. So what we're gonna solve is where we cut these are the members we're gonna solve right here, okay? That's what we're gonna solve. I'm gonna redraw this just a little bit bigger and get rid of this, so give me a sec here. Actually, I'm just gonna go ahead. Now you're gonna need to help me make sure I get the forces in there right, okay? So give me a few seconds here to do this. So I can draw this a little bit bigger. Let's see, what did I say that was? 6 and 8. Calculator here, hold on a minute. So I just wanted to check something. All right, I'm gonna get mine. So I'm gonna draw this just a little bit bigger so we can see it. Okay, there's my simplified free body diagram. Now, since we're working, we decided on the left side, we have to bring in all the forces. So the first thing I'm going to do is put in my reaction. And I actually have 2. Even though the one's 0, I'm going to do the accountability on that. I'm going to account for it. And then we only have 2 forces that are coming in on this guy. One here and one here. Let me go ahead and label them, and then we'll analyze it and make sure what we've got. Okay, so there's a reaction, and here's a reaction. Okay. This guy was 6 kips. This guy is also 6 kips. Okay. And I'm going to do a real quick section cut through here. Okay, so this diagram is pretty all critical. Oh, I hadn't put everything in here yet. So I know that this is 18 kips, and this is 0. Does everybody agree with that?
Yeah.
Do I have any forces missing or any reactions missing? Any external loads missing or any forces missing or reactions?
No.
Is there anything that you think should be added? Like there's other forces out here, right? Sometimes people try to put those in. Notice those can't be in on this section cut, but they would be on the other one, right?
Mm-hmm.
Okay, so once you've done that, then you have to determine whether these guys are in compression or tension. You just make a guess, okay? Now, I don't even mess with it. Like I told you, you can kind of look at it on the joints and you can kind of figure out what's going on. I don't even care. I just make everything tension. It's just easier for me. So I'm just going to say, just make everything tension, okay? Don't worry about which its direction. And you know it can't be tension. Everything can't be tension. So you know one or both of those are going to be compression, but that's okay. But we'll go ahead and label this. This is section, or this is member BD up here. This is member CD. And this is member CE, okay? So I cut through my section completely. I just modeled them all in tension, brought in all of my forces, and now I'm ready to apply my method of sections. Okay, is everybody okay with that picture? Because that picture is all important. And if the reactions we blew, we're in trouble too, okay? And also remember, this was 8 feet. We're gonna need that number, and that's the same thing over here. Top to bottom, it was 6 feet, wasn't it? Is that
Yeah.
right? Okay. So you got to have those numbers in mind too, because when you get into your doing your moment equations, you're going to need those. Okay. All right. So we're ready to do the first piece. Sum of forces in X. So sum of forces in X is equal to 0. So what do we have going on in X? BD, CE horizontal, or CD horizontal, and CE. Everybody agree with that? Nothing else external load, right? So we have BD plus CD horizontal plus CE, and all of that has to equal what?
0.
Right? So you can see right now, those can't all be in tension, right? That's impossible. One of those has to be 0 or negative so that it can cancel other ones out. So we know we've got an issue, but that's okay, all right? We don't worry about it. But this equation gives us Zippo, right? And nothing, absolutely nothing, right? So we're going to have to go to another equation here. Let's see what sum of forces in Y do for us. Okay, so sum of forces in Y, we have 18 up minus 6 minus 6. What else? No forces number, no, BD doesn't give you any vertical. CE doesn't, but CE, CD does. So that will have a positive CE vert. And that's equal to, I'm sorry, let me back that up. Yeah, I blew that, didn't I? It should be CD. CD vert. And that's going to be equal to 0. Now that's solvable, isn't it?
Yep.
So you get positive 6, and it comes over as a negative 6, right?
Mm-hmm.
So what does that tell us?
It should have been compression.
Right. So, but we're not going to change anything. Okay. We're going to let it go with this, but we're going to make sure that we feed the negative signs through. Okay. So can we resolve CDH knowing this? Well, we know that this member is acting over a distance of what? 8 and 6, right?
Yeah.
So the vertical member, the vertical component is to 6 feet as the horizontal is to 8. So we can write an equation over here. CD horizontal is to 8 feet as negative 6 In other words, compression is to 6 feet, right? So when we solve this relationship here, what are we going to get? What's that give us? Horizontal component is to 8 feet, negative is to 6 feet. What's that give us? No one can solve that? Proportion? 8 times negative 6 divided by 6?
-8.
Negative 8. Okay, so when we come back into this equation, we're going to plug this in as a negative 8. Okay? But we still have 2 unknowns, so there's no point in putting that in there yet. Okay? Does everybody see what we've got? We have one member right now, and we know that it's in compression. But we have to solve the rest of these. Okay? All right, so I'm going to take a moment, sum of moments, and I know that the sum of moments about any point have to be equal to 0. So here's where we want to be smart. I want to take a moment at such a point that I knock out unknown forces and just solve one force. Who can tell me where a good place to take a moment might be? Now, you can literally take a moment any place on that truss, even off of that truss section cut. Okay? So who can tell me might be a good place to take a moment? Max, you got an idea?
Not entirely. All I would say is A, where
Over here?
either, yeah.
Okay. The problem with taking it at A is I would still have this unknown and this unknown. So I'm going to have 2 unknowns. So A would not be a good place. Okay.
Mhm.
Anybody suggestion?
C.
C, right here. That's C, right?
Yeah.
Now what's good about that is the line of action CE runs through the moment, the line of action CD runs through the moment, and BD is going to be resolved. Now we're going to lose 6, right? And 6, but we'll still have 18. So C would be an ideal place. Anybody see another place that would be good? That's a great place, by the way.
B?
B is up here, right?
Yeah.
B, again, would keep, it would give me 2 unknowns, essentially. But if I went over here, do you notice these lines of actions, if you follow them up, they would go to D?
Yeah.
Okay, if you took a moment at D, you would lose BD and CD and solve CE. Okay?
Okay.
So either D or C would be absolutely great places to take moments. Okay? So since Jacob, you suggested C initially, why don't we go ahead and do it there? Does that sound good?
Yep.
Okay, so we're going to do a moment at C. Now remember, we're going to lose these 2 forces because they're coming through it, okay? And we're going to lose CD and CE, so you have to be really careful when you do a moment. That's the only thing, okay? We also lose this guy who's 0 anyway, but if he had a force coming through, that guy's gone too, that reaction, okay? So I'm going to start here, and I know that this is 8 feet times 18, and that's tending to turn it clockwise, right? So that would be a plus 18 times 8. Force, distance, and that's the direction of rotation. Also, remember the 6's are gone, so the only thing that's left is this guy right here, BD, right? And BD is a distance of what from that moment? That's 6, right? 6 to the line of action, BD. Do we agree with that? We're sitting here. Line of action is up here, right?
Right.
So we got 6 times BD, negative or positive rotation. If you put your pin right here, it's tending to spin that what? clockwise, correct?
So positive.
So it's going to be positive 6 BD. And all of that has to equal what? 0. All right. So let's look at that moment. Do we have every force and every moment accounted for? Because these are gone and these are gone. You just really only have this guy and this guy. And that's the 2 moments that we're dealing with, right? So if we have 8 times 18, that's a positive 144. It's going to come over as a negative 144. So this is going to yield for me BD is going to be equal to negative 144 divided by 6. Okay, so when we have that negative divided by a positive, what does that tell us? We get a negative, right? Does everybody see that?
Yeah.
Yeah.
So what is happening with BD? Is it tension or compression?
Compression.
Yeah, because we modeled it initially as tension, and this is saying, no, you're wrong. So we don't change anything here, remember, but we just are going to call it compression, okay? That's what you would do there. So now you can solve CE, because in this equation, BD is negative 24, so we're going to just feed negative 24 in there, and CDH is negative 8. So we feed that in there with its sign. Can we solve this now? And 24 plus 8 gives us a negative 32, but it comes over what? As a positive 32. So that one actually is indeed what?
Tension.
That's a tension. So that's the only one that's been tension. The rest of them have been compression. Okay, so we need to solve CDH yet, or CD rather. So CD is 6 squared plus 8 squared square root. Ooh. What'd you get? 10? 10 kips?
Yeah.
And that should be what? Compression or tension?
Tension.
No. What's this saying right here? The negative's indicating that it's not what we indicated, right? We called it tension, but this is telling me it's not. This is never going to be negative because when you're doing this in a square like this, it's always going to be positive. When you square a negative number, you're always going to be positive. So this is actually a compression member. Okay? You guys with me on that?
Why is that again? Why?
Up here, Jacob, when we solved CDV originally,
Oh, okay.
it told me it was negative. So this has to be compression, okay?
Okay.
When you're doing a Pythagorean theorem, if you square a negative number and square a negative number, you're always going to get positive here, okay? So that's just giving you that raw value, but the quality of that is coming from the solution of what we did up here, okay? You guys see that?
Yep.
I want to show you something. You don't need to do this, but I like to do this sometimes as a proof. If I independently solve CE using a moment, I should come up with 32, okay? So I'm going to do another moment. Now, you don't have to do this actually, but I'm going to just to show you, I have a proof on this that what I've done is correct. So if I take a moment up here at D, okay, what I'm doing here is I'm canceling out BD and CD. I'm acting like I don't even know what they are, okay? And I'm going to resolve this, and if I don't get 32 tension, I know I did something else wrong. You guys see what I'm saying? So it's just going to be, is this going to kind of be a proof on the whole process? But you don't in reality, when you do these problems, have to do this, okay? So if I'm sitting here, okay, that's 8 plus 8 is 16 to that 18. It's still turning clockwise. So I'm going to have a plus 16 times 18. All right. Now this one's going to be a little bit messier from a moment standpoint. If I'm sitting here, it's going to be 8 times 6, and that's going to be a negative. 8 times 6, whoops, I just, negative. Negative 8 times 6. Got to get your moment signs right. This one also, from sitting here, that looking at that one, it's also tending to turn that way. So that's also going to be a negative 8 times 6. We could have also combined those in 8 times 12 and done it in one. And then the last one we have here is CE, which is tending to turn it negatively. So that would be a negative 6 CE, and that has to be equal to 0. So this moment, if I've done everything right, better equal 32, and it should be a positive 32. Let's see what happens. Okay. So I get a positive 192, comes over as a negative 192. You guys check me. Divided by a negative 6. So negative divided by negative is definitely going to be a positive. I get 32. So this just checks against that, okay? But you don't have to do that if you don't need to. Absolutely, you've already got your answers, assuming you think that everything's correct. This just kind of gives you a proof over the whole process, okay? Did everybody see what I did there?
Yeah.
So typically you can solve section problems with a sum of force in X, a sum of force in Y, and a sum of moment. That's all you absolutely need when you do these, okay? So sometimes you do require 2 moments. It just depends on what you're doing. Sometimes these problems will require 2 section cuts. It depends on which sections they're actually looking at. Now the whole problem, again, I want to state this, and this is emphatically, you got to understand, everything in here is based on this guy right here. If you blew your reactions, you're going to get answers in here, but nothing's going to check. Even though these guys might check with each other, this is going to give me answers no matter what I feed into it. Okay, so reactions are all critical. They're all critical. Okay, you guys good on that?
Yeah.
Yeah.
I'm going to go to and we're going to do another problem. Okay, and I'll show you some really cool things about sections that you don't even need to solve reactions all the time. It just depends on how the truss looks. So give me a minute to draw one up. Okay. So I'm going to start a new image. And let's see, let's see, give me a sec here. Give me, Okay, so we're gonna have a load here and a load here. Okay, so that's actually not a member. I'm just gonna get rid of that real quick. So we have a load here, 6 kips, a load here, 6 kips, and a load here that is 9 kips. So all these guys are kips. And up here, we have a reaction. There's a pin, and you could have a roller down here. Okay. And let's see. Let's give you some distances. This is 8. Oops. What's going on there? Oh, that thing's still turned on. 8 feet, 8 feet, and this is 12 feet, but we're assuming that's symmetric, so it's going to be 6 and 6. Okay, so this is A, this is B, C, D, and E. Okay, does everybody understand our truss?
Yeah.
Okay, so let's say we need to solve members AC, BC, and BD. Okay, so that would be over here, right? AC, BC, and BD. So what I'm essentially saying is I could take a section cut right there. Does everybody agree with that?
Yeah.
Now, what do you notice about this? If we take the section cut on the left side, what we are dealing with is reactions. Does everybody agree with that?
Yeah. Like on a problem in the book or like on a test or whatever, would it always say you need to solve like AC, BC, BD, so that's where you like know where to make that cut?
Right. They do say that, but here's the thing. They might say you need to solve AC, BD, and CD. So you're not going to be able to take a cut that's going to go like that. You're going to actually have to do 2 cuts, okay, sometimes. So very often problems in the book, you're going to be required to take 2 cuts, okay? You can't take a cut that's outrageous because what will happen is you won't be able to solve it. But you can do like a diagonal cut, so you could take a cut like this sometimes, okay? But you couldn't do something like, let me undo that. You couldn't do something like this where you come through, cut like that, and cut down. That would be an outrageous cut. Everybody see what I'm doing?
Yeah.
That would be completely unsolvable. But a cut like that might be solvable. So you could look on this side or you could work on that side. So it just depends, okay? So yeah, you'll always be told what members to cut, but you won't necessarily, or to solve, but you won't be able necessarily be told what section cut you're doing, okay? That's a good point, all right? Any questions on that?
Nope.
So back to this real quick now. If we take the section cut here, we can either work on this side of the truss, which requires us to solve reactions, or we can work on this side of the truss, which doesn't require us to solve reactions. Does everybody see that? let me do this. Maybe you'll be able to see this a little bit cleaner. Let me undo this. I'm going to put me a nice section cut tool. I like my little section cut tool. There we go. All right. There's my section. Do you notice the reactions are gone? Everybody see that?
Yeah.
We don't even have to solve reactions. What's cool about that? You don't have to worry about blowing reactions, do you? If you have the tendency to not be very good at reactions, you just negated that. You don't have to worry about it. So now we can solve this member, which is AC. We can solve this member, which is CB, and we can solve this member, which is BD. Now, I'm going to tell you, you can't always do that, okay? Like that truss we just worked on before, you had to solve the reactions, but this one we don't have to, okay? Now, it looks like a mess, but we're going to see it's not that big of a deal. Is everybody okay before I go on?
Yeah.
Yeah.
Okay, so what do? We write what? Sum of forces in X, sum of forces in Y, and sum of moments, right? And remember, you want a moments, you got to work smart, okay? So I'm going to go ahead and do my sum of forces in X first. That's usually pretty straightforward. So there's no vertical forces that are external, so everything's coming in X, Y. It's based on those guys. So we have minus BD, and then we're going to have minus CB horizontal, correct? And then this guy will bring a minus AC horizontal, and all of that has to be equal to 0. And again, what that's telling me is, well, one or both of those have to be, two of them have to be wrong, because all those negative numbers can't equal 0. So we know that we've got something mismatched, but that's okay. So let's see what happens when we do a sum of forces in the Y. Sum of forces in the Y have to equal 0. So what we're going to have is minus 6, minus 6, minus 9. And then what do we have in the vertical unknowns? We're going to have a negative CB vert. And what about AC? He'll bring in a component of what? Positive AC vertical. All of that's equal to 0. Do you guys agree with my setup?
Yeah, it looks good.
Okay, so this, when we sum these, that becomes a negative 21, so we can bring that over as a positive if we want. So essentially, this tells me negative CB vert plus positive AC vertical is 21 kips. But we know nothing about the distribution of those, right? So I'm going to take a moment. And I'm probably going to have to end up taking 2 moments. I might want to drop that down just a little. All right, so I'm going to take a moment. All right, you guys tell me. We want to take a moment at a smart location. What's going to be a good location here? There's one real obvious location if you look at it. Nobody has a suggestion?
C.
Absolutely. Why do you say that, Max?
Because that's where AC, CB, they all,
Right.
and what's the vertical one right there?
This guy?
Yeah.
Those are just external loads. So
Oh,
you're going to
okay.
lose those too, but the key thing is what you're going to do is lose these two, right?
Yeah.
And that gives me one unknown. That's a really smart place, okay? Now the other smart place is to take it down here at B, but you're still gonna have to do something. You're gonna have to use transmissibility to solve this, okay? So that's a little trickier. So let's do C first, because it's a little cleaner. But remember, all we're gonna get out of that is BD. That's still not gonna get us enough information to either solve this or this, but it'll give us one more piece of the puzzle. So I'm gonna go ahead and take it at C. That's a really good spot. But remember, we're gonna lose these guys because they come through the line of action too. But that's not a problem, right? Not a problem. I want to also note that this guy's 6 feet because it was symmetrically 12 from top to bottom. So this is 6 here, okay? So you might want to add that on your diagram. So this is 8 on 6, and this was 18 on, or 16 on 12 is what that actually was, okay, initially. Okay, so I'm going to start here. If I'm sitting here, I've got 8 feet over to that 9 kip load, and that's tending to turn that clockwise. So that will be a plus 8 times 9. Okay, that's 8 times 9 for this guy when I'm sitting here, right? The 6 is gone. The 6 is gone. The 2 unknowns are gone, diagonal. So all we're left with is this BD, and this is 6 to his line of action, okay? And he's also tending to turn this guy clockwise if I'm sitting there. So that will be a plus 6 BD. All of that has to equal 0. Now what you should notice, since I have both pluses here, that's going to give me a negative answer. And that's okay. It just means it's going to be in compression, right? So 8 times 9 gives me a 72. It's going to come over as a negative 72. So we get negative 72 divided by a positive 6. Gives us a negative 12. So we know that BD is a 12 kip load in compression, but it's the negative. So when we use this back here, now notice when we plug this guy back here and a negative into a negative, this guy will become positive on this side of the equation. Okay. So we still don't have a resolution, do we? So what are we going to need to do here? We're going to have to end up taking another moment. So this is where it gets a little tricky, but if we take the moment down here at B, and we bring this guy up through transmissibility, what that'll do is transmissibility will lose the vector AC vertical, but it'll give me the horizontal vector. So I'm going to try to draw this for you a little bit, but I'm going to take a reaction or a point down at B. I'm going to clean this diagram up a little bit. Let me I'm going to move this guy over so we can see this a little bit better. So this is BD here, and this is BC or CB. And I'm going to move this guy too, just out of the way so we can, oops. So this is AC. Okay, so now I'm going to, let me just kind of do something here, because this will help you visualize what's going on. So I'm going to kind of, if I take this guy's line of action like that, and that guy's line of action, and that guy's line of action, what we're doing Okay, so this is actually point B down here. Does everybody see that? Can you guys see that?
Yeah.
All right. Now this is kind of the tricky part of this whole process here. Let me put this back. Up here, this is actually point A. There's going to be two vectors associated with this. One going that way, and one going that way. So this turns out to be AC vert, and this turns out to be AC horizontal. What I'm using here is transmissibility. Does everybody see that? Remember, we can slide this guy anywhere along that line of action, correct? We could also slide it this way if we wanted to. You could go either way. Does everybody see what I've done there?
Yeah.
So AC vert's line of action does what? It comes through what? The point of moment, right? Everybody see that? So the only thing that's left here is going to be ACH. So this moment at B is going to knock out CB, CD, and AC vert, and what I'm going to solve is ACH. A little tricky, right?
Yeah.
But what you've got to think about is that concept of transmissibility. Okay, remember, transmissibility says I can transmit these forces anywhere along that line of action that I want to. I could really bring them down here too, and by doing that, I could solve ACV as opposed to ACH. Okay, does everybody see that? Let's see if we can write the moment equation. Okay, so if I'm sitting here and I look at this force, that force is a distance of 6 over, or 8 over, excuse me, and it's a clockwise moment. So we're going to say plus 8 times 6 for this guy, right? And then we're going to have this guy is also a plus 8 times 6. And this one, the 9 kip load, is going to be 16 over. He's also turning it clockwise. So that's going to be plus 16 at 9. Okay, so external load moment, external load moment, external load moment. So now this guy, remember, because his line of action is coming through my moment, because I've used transmissibility to do that, he's gone. So the only thing that's happening here is ACH, and this distance is 12, because it's 6 here and it's symmetric, okay? So this will be minus 12 ACH is equal to 0. So this thing solves now, right? This will solve. So what we get, let's see what we get. 8 times 6 plus 8 times 6 plus 16 times 9. I got a 240. It's going to come over as a negative 240. So ACH, negative 240 divided by a negative 12. I get 20. You guys agree with that? Positive 20.
Yeah, that's what I got.
Okay. So if you got positive 20, right? That tells me that this member is what? The positive sign agrees with this way we're facing this, right? So that tells me this is a tension member, correct? We agree with that?
Yeah.
Okay. So watch what we can do now. So knowing ACH, we can plug this stuff in here. So we've got BD is a negative 12. when you plug a negative 12 into here, that goes to a positive 12, right? Here. And you've got minus CBH, and you've got 20 that gets plugged into that negative location, so he remains negative. All of that's equal to 0. So let's see what happens when we solve this. 20 negative, 12 minus 20, you get a negative 8, comes over as a positive 8. So what is this saying right here? Negative CBH is 8, right? Is that correct? So if I multiply through by a negative 1, what does that tell me? Let me do this. It tells me this is actually negative, right? Did we agree with that? Just plug these in, right? Solve for that. You guys okay?
Yeah.
Okay, so that tells me that CB is a compression member, AC is tension, and we already know that BD is compression. So how do we actually solve AC and CB? We just have components of them, right? So can't we write a little proportion for these guys? So if we look at CB, we know that the horizontal is to 8 as the vertical is to 6 feet. So I can come up here and I can say CB vert is to 6 feet as negative 8 kips is to 8 kips horizontal. So what does that give me, sir, for CB vert? 8 divided by 8 is a negative 1 times 6 gives me a negative 6. Okay, everybody see that? So we can solve CB. 6 squared plus 8 squared, square root. That gives us 10 kips. And because both of those guys were negative, that's a compression member. Let's see, okay? So how do we solve AC then? I lost you guys. Max, you okay?
Yeah.
Okay, so that doesn't sound too good. Where did I lose you?
No, I'm not lost. I'm just trying to process this kind of.
Okay. It's just you're really just looking at the some forces of X, Y, and moments. But then sometimes we had to take 2 moments in this problem. So even though we didn't have to deal with reactions because we had a lot of stuff going on here, we had to deal with 2 moments to solve it. Okay, so it's a lot of just keeping track. And the other thing is too, with all of these guys, probably more so than with joints, you got to really watch your signs. Signs are going to be all critical, but that's always true. But when you feed that stuff back into these equations, you got to make sure you do it right. So I had a negative 12, a negative into that negative becomes positive. But where this one was a positive number, when I fed it back in, became negative. So you just have to watch that. And then your sign here was critical because that told me it was compression. So I'm over here. So how do we resolve AC? We need a vertical component, don't we? We have a horizontal component. We could use the same method here. We could use a proportion, or we could actually solve it up through here because we know CB vert. So we could solve ACV using that method, either one. So you guys have a preference on how we do it? Well, I'll solve it through this. What I'm going to do is erase. I'm going to get rid of this right now. Just put that out of my way. Okay, so if I look at this equation up here, I know CB vert is -6. When you plug a -6 into this, that becomes a 6. So that'll be 6 plus AC vert is equal to 21. So therefore AC vert will be equal to 21 minus 6. Gives me 15. This has to be positive, by the way, because this is positive. If you get a negative up here, and that's a positive, you got a problem, because that would mean your diagonal is facing a different direction. Okay. Did everybody see what I did here? So now we can solve AC itself. AC 15 squared plus 20 squared. And that would be equal to 25 in tension. Okay, so we have AC, BC, and BD. So there's your solutions. Okay. You guys want to check out another problem? Or you think you got it?
I think I'm pretty good. Are we going to be able to go through one on Thursday before the test too?
Absolutely. I think that test shouldn't take you more than 2 hours. Okay. So you're going to have 2 problems on the test. One is a joint problem and one is a section problem. Okay. So if we get there at 8, we get started right away. We might even be able to go through 2 problems. Okay.
Okay.
So you'll want to work the problems that are assigned in the book before we get too far into that. But we can do another problem here, or you want to do a joint problem, whatever. We got time yet today, so you tell me what you want to do, and we'll do it. Do you want to look? You want to go ahead and do that one joint problem we talked about before or come back to, or do another, or do one more of these. I don't really care. I can do one of the book problems with you if you'd like.
It doesn't really matter. I honestly feel pretty good about both of them.
Sections is actually, you've got to just go, you're going to have to do some homeworks for me, okay, between now and Thursday. But I think you'll find it's actually, it's simpler than the joint problems. The only thing with this that you got to watch is you've got to be smart with your moments, okay? And this one was a little tricky because you had to use that transmissibility, but that's not typical. Most of them you don't have to do that, okay? But we're going to be looking at, I'm going to have you guys do problems, basically the problems from like 9, problem 9, 10, 11, 12, 13, 14, 15, up to 17 actually. So you can do all of those, and those are all joint problems, or section problems, excuse me. Jeez, I keep. So those are all, they'll all be straightforward. If you can work through them, as many as you can, that would be good, okay? And then I've got office hours tomorrow from 8 o'clock until 1 o'clock. And even in the evening, you guys can shoot me questions if you want, and I can help you out with that. So that won't be a problem. Okay.
Okay.
So do you want to do a joint problem, Max? You said you want to do problem 5. You want to go ahead and tackle that?
Yeah, sure.
Okay. And while, when we get done with that, if you guys want to take a look at another section problem, we can, okay? So I'm not trying to make this, I want to make sure that you get enough instruction out of this so that you're able to do this, okay? And feel good about Thursday, okay? I mean, it all comes down to how many problems you've worked, though, okay? If you worked a bunch of problems, you'll be in good shape. So I'm going to go ahead and clean the screen up here, and we're going to take a look at problem 5 out of the book, which is a method of joints problem. So it's a little bit longer winded, okay? Give me a few minutes to draw this up, and then we'll get started, okay? So this truss is doing something. Oops. Okay, so why is it? Give me a sec. This thing sometimes doesn't want to cooperate with me. Now, let's see. No, not in a mode. This thing will turn itself off to an erase mode sometimes, and give me a sec. Pen's great when it works, but sometimes it turns itself into a different mode. Okay. Let me try getting out of here a minute and get back in. Still not working. Good. Okay, now we got it. Okay, so the first thing I got to do is draw this so we can get our reaction. So let's go ahead and get that going. $30. This thing's got a lot of geometry associated with it, so you have to be real careful with it.
What page is this on in the book?
It is page 151. 151. So let's see, we got this guy coming up like that. And there's a truss member here. Okay, so basically it's a triangle like that, but then it's broken down into thirds. Let me see if I can eyeball thirds in here. Best I can. That's pretty close, I guess. And we got a member here, or a load here, a load here, and a load here. And then we've got oops, this guy over here. We've got another member coming in like this. And another member here. Like that. Okay, so there's my truss. Let me get my loads on there. Load here, load here, load here, Oop, wait a minute, there isn't a load there. Let me get rid of that. That would change the whole scenario. Okay, so just two loads. We have an external load here and a 14 kip load here. Okay, so the panels are 10 feet, 10 feet, 10 feet. We also know it's 10 feet here. So we have a pin at the top and a roller at the bottom. Go ahead and put this is D, C, B, that's A here, and G. Okay, so what do you think is going on with this pin? Well, we got vertical component, right, and a horizontal. One like this. And one like this. So which way do we want to react these? Vertical, up or down? Want to go up or we want to go down with it?
I'd say down to the left.
Down and to the left. So you want to go like this?
Yeah.
Okay. So that's my reactions. That's going to be RGV, right? And this will be RGH, correct? And what about that roller? Which way is he reacting? Left,
Left.
right, up, down? Is he this way or is he vertical?
Wouldn't it be horizontal?
It would be, because notice that the surface over which it's rolling is a vertical surface. So the roller has to be, the reaction has to be perpendicular to that. That's correct. So the question is, do we make him left or do we make him right? And the
Left.
reality is it doesn't matter, right?
Right.
Okay, so what do you want to call it?
RAH.
Which way?
Oh, left.
To the left? Okay, you want it like this, right? Is that what you're saying?
Yeah.
Okay, so this is RAH. Okay. All right, so let's solve the reactions. So we have sum of forces in X. In X we have minus RGH minus RAH, and that's equal to 0. So you see that's an impossibility, right?
Yeah.
But it doesn't matter. So what we're going to do is we're just going to say R. Actually, I'll do this. I'm going to say let me do this. I'm just going to bring that guy over. So that'll say RGH is negative RAH. That should make sense because they have to be opposite, right? But we just don't know which way they're going yet. Okay? Does that make sense?
Yeah.
Okay. So sum of forces in the Y have to equal 0. So we have indicated RGV going down, right? So that's a negative. Then we have minus 8 and minus 14. All of that's equal to 0, correct?
Yeah.
So what's happened here? If I bring RGV over, it gives me a positive RGV is equal to a negative 22. So what does that tell us? RGV is not acting down, it's acting what?
It's acting up.
It's acting up. So we made a mistake, no big deal. We're going to correct it when we get into the joints, okay? So we're good with that. Okay, so we need to take a moment. Summation of moments. Where do we want to take moments?
Say G.
Okay, G is good. G is going to knock out RGV, RGH. We'll leave 8 and 14. And it's going to solve, it's going to resolve RAH for us. Excuse me. So we're going to take, let's see, I'm going to look at this point. That's going to be 10 times 8 positive rotation plus 10 times 8. Okay. Then this will be 20 times 14 positive rotation. And then this will be a positive rotation at 10. So that's going to be a plus 10 RAH is equal to 0. So we're going to have what? 8 times 10 is 80 plus 20 times 14. I get a positive 36. That's going to come over as a negative 36. I'm sorry, 360, not 36, 360. So those give me a positive 360, comes over as a negative 360, divided by 10, gives me a negative 36. So what does that tell me? What does that tell me about RAH?
Down. Oh wait. I'm sorry. I don't know why I said that. It's left.
It's to the left, so it's actually going, well, no, it's, you already said it was to the left. So what it's actually telling you is it's doing what? It's going to
Tension.
the right.
I'm so confused. If it's negative, how come it's going to the right?
Well, we modeled it as a negative initially, right?
Right.
But remember, this told me, nope, it's not going to the right. It's going opposite to the way you said it was.
Okay.
Okay? Just like this one told us, we modeled it going what, down? And the negative said, no, it's not down, it's going up.
Okay.
Okay?
Yeah.
You made an initial condition, you made an initial assumption, but this is telling me your initial assumption is incorrect.
Okay.
Okay? That's what that's saying to you.
All right.
Okay?
Yeah.
So when we plug a negative 36 in here, that tells me that RGH is what? Positive 36,
Yeah.
right? So that says to you what? That your initial assumption was correct.
Okay.
Okay, does that make sense?
Yeah.
All right. Okay, so here's what we're going to do. Before we get into this truss, we're going to correct everything, okay? So we know the number of RAH, right? We just solved it, right?
Yeah.
But it's not going to the left, it's going to the right. So we're going to correct that here. We're not going to call it negative though, all right?
Okay.
We want to get rid of the negative sign when you get into these problems. Now RGH was correct, right?
Yeah.
So the direction of that arrow is good. And now we're just going to replace that with the value of 36, okay?
All right.
And then we need to do the same thing up here, but we have to correct his direction, right?
Yeah.
Because he's actually going up. And if you look at this, this should make sense now,
Mm-hmm.
the way we've got everything going, okay? Are we good now?
Yeah.
Okay, so we have to do one more thing. We're going to need distances here and here, which we don't have to be able to solve this truss. So here's what you have. You have a similar triangle. This triangle and that triangle are what they call similar. And that triangle and that triangle are similar. So what you're saying is you have a side of 30 on 10, and this triangle would be 20 on X. So you're saying that 10 is to 30, 10 is to 30, as x is to 20. So I'm looking at that triangle compared to that triangle. Solve that proportion for me. 20 times 10 divided by 30. What do you get? Solving for x.
Got
What do we get?
6.66.
Probably 6.67, right? If you round it to 2.
Yeah.
Okay, hold on a minute. Okay, so what we want to do is we want to call this distance here 6.67. So from there to there at 6.67, we can do the same thing. 30 is to 10 as 10 is to x. So 30 is to 10 as 10 is to x. When you solve that proportion, I think this comes out to be 3.33 essentially. Okay. Do you agree with me?
Yeah.
We needed these numbers because notice when we get into this slope on this guy, we've got 10 on the horizontal and 6.67 there, and now we've got 10 on 3.33. So we needed those numbers. Okay.
Oh, I see.
Yeah. Okay. So now, after all of that, now we're ready to actually start attacking the problem. Okay. So our question is, where do we start? You know, with a joint, that's always your question. Where do you start with a joint problem? Well, you got to start with something where you're going to get answers, right?
Yeah.
Yeah. F is, there's nothing here. There's too many unknowns here, too many unknowns here, too many unknowns here, too many unknowns here. So you're really limited to probably G. And actually, it looks like D has too many unknowns, but D actually would solve. So you could either do D or G. Did you have a place you started, Max, or did you even try it?
I got confused. So, can we just start at G?
Yeah, absolutely. Yeah, but we couldn't start at any other place other than G or D. So if you tried to do any of the other ones, sometimes people might try down here, but you would find pretty quickly that that's not going to work. Okay.
All right.
All right, so I'm going to start at G. I'm going to have to erase these pictures, okay? So you guys can just remember what you got, or you may need to give me some numbers, okay? So let me just go ahead and, all right, so I'm going to go ahead and I'm going to do my joint at, G. So I'm going to try to do 2 joints on a page. Let's see. So I know that I've got a reaction. Come on. And I've got another reaction going like this. And then we've got a member here. And then we've got a member like about right there coming out. So we have a diagonal member, which is actually is a good thing. Okay, so let's see. This guy reaction was up, right? 22, is that right? And this reaction was 36 going that way. So remember, we're doing joint G. Okay, so we have member GA and GF. So can you determine anything about the direction of any of those guys? You want to look at the diagonal, right? That's the one that could tell you?
Yeah.
Okay, so the diagonal horizontal of this guy can only counteract that guy, right? Because this guy has no horizontal. So what do you think? Compression or tension on him?
Tension.
Okay, I would call him tension too. So that would be GF. Now, I'm not really sure what this guy's doing. He's going to have a downward force. He's going to have an up. You just got to decide whether you think it's going to be up or down. Do you have a suggestion? I don't really care.
Down.
Okay, we're going to call it down. That's fine. Now, we're pretty convinced that this is going to be tension. You agree with me?
Agreed.
Okay, but this one, that's, I don't know, but we'll see. But it'll tell us, right?
Mhm.
So now, in joints, remember, we only have two equations, sum of forces in X and sum of forces in Y. And if we can't solve it with that, we're done.
Mhm.
So let's see what happens. We're not done with the problem, we're just done with that joint, okay? So in X, we have what? Minus 36 plus GF horizontal equals 0. That resolves, doesn't it?
So then it would be positive 36.
Yeah. So that tells us that it is truly what? A tension member, right?
Mhm.
So we guessed that correct, okay? More than a guess. That was a little bit more educated guess, right? So, okay, so we can write sum of forces in Y up here. So in Y, we're going to have 22 up, oops, 22 minus GA minus the GFV, all of that has to equal 0. So we can say this is equal to a minus 22. Is that right?
Mhm.
Basically, you can say this, right? So I can just keep it simple if I want to do that. Agree with that?
Hold on. Yeah.
Okay, just flip them. So now look, we've got a GFH, so we should be able to get a GFV. And if we get a GFV, then that'll solve here, and that'll give me GA. So now we have to be really careful with this, because we know the distance over which this is acting horizontally is 10. Does everybody agree with that? You have to go back and look at your original diagram. Isn't this guy acting over 10?
Yeah.
What's the vertical though? That's a tricky part. Well, the total vertical from A to G was 10, but we're only looking at the vertical distance over GF. So what happens is, I'm going to draw a little diagram here. This is where you got to think about it a little bit. Ah, damn it. I'm going to draw that out a little bit. I'll get there, hold on. Okay, so this distance on this diagram is 10. And that distance right there is 6.67. So this distance here is what? 10 minus 6.67 gives us what? Does everybody see what I'm doing there?
Oh, yeah, I see.
So this distance horizontally is 10, but the vertical component of that is 3.33. That's the one you have to really watch when you do this, okay?
All right.
All right, so my proportion here would be GFV is to 3.33 as 36 is acting over 10, okay? You guys got that? Based on this little diagram here. That's the thing you got to watch on these trusses. So let me turn that off. So GFV FV will be equal to what?
I got 11.98, so 12.
Yeah, and that's the one thing because we're gonna have a little bit of rounding going on here, so don't expect everything to just work perfectly at the end. I mean, you might not come exactly to zeros. Okay, so I'm still hold on a minute. I'll be right with you. Yeah, so it's 11.98, but we're just going to call this 12. We agree with that?
Yeah.
Okay. Let me erase this picture. Keep that picture in mind though, because that's a critical kind of thing. I don't think we'll have to do that quite as much. Most of the numbers will be there now. Okay, so that gives us the ability to now solve GA, right?
Mhm.
So GA 22 minus 12 gives us what? 10?
Yeah.
GA is positive, right? Is that correct? You plug in 12 here, comes over as a negative. That's still positive 12, 10 rather.
Yeah.
So what does that tell us about GA?
It's going up.
It's going in the way we indicated it, right?
Yeah.
So it's definitely a tension member.
Okay.
So it is tension. And the other one was correct too, wasn't it?
Mhm.
So now we can solve GF using the Pythagorean theorem. 12 squared plus, what was it, 36 squared?
Yeah.
And that gives us GF, also tension. So both of those are tension members. So 12 squared plus 36 squared square root. Basically 38. You could call it 37.9 if you want. I'll just call it 37.9. Compression or tension?
Tension.
Yeah, positive here, positive there. We indicated it tension initially, so both of those are tension members. Okay, so you have this guy and this guy. Okay, so now which joint do you think we could roll to?
D. Yeah. D.
D, we could go to D. I actually think we could probably solve A as well. Do you want to go to D? It's your call. Just keep in mind what we got solved, okay?
No, we're right there. Let's just do A.
Okay, I mean, I'm not trying to sway you. If you
No,
want
I
to
know.
do D, we can do D. Okay, so we'll go A then?
Yeah.
Okay. So A, we're bringing in, let me put A here. So there's A. Give me a sec here to draw it. We have a vertical component that we just solved. And we have a horizontal component and a horizontal reaction. So what's going on here is we have a reaction on this guy. And we have an unknown. And then we also have, let's see, we have a member coming in. That's at, let me draw that a sec. So that would be what we've got going on. So let's see. The member coming down, GA, was a tension member, right? So this guy, this is GA, that's tension, and we just said that's 10. We have a reaction here, and that reaction was doing that, right? What was the reaction of A? It was 36, wasn't it? That was the reaction.
Yeah.
Yeah, okay. All right, so now we've got two unknowns here, and we just need to determine directions. And if you don't know, just make them all tension, all compression. But I think like I said, if you look at this one, you can determine what's going on with the diagonal.
Mhm.
What do you think?
I'd say compression.
Right, because this guy can contribute nothing to the vertical. So if that guy's going up, this guy has to be going down. So therefore, this has to be a compression. Okay, so that's going to be, we're going to call that AF. Now, what about member AB?
Compression.
Compression? Okay, we'll call it compression. And I don't really have a clue on it, so we're gonna say, we'll see what happens when we resolve it. So let's see what happens. All right, so we're gonna do a sum of forces in X, have to equal 0. So in X, we've got 36 minus AB minus AFH is equal to 0. So what that really tells me is AB plus AFH is equal to 36. So I'm just bringing those guys over here and swapping them, okay?
Mhm.
All right, I like to get rid of my negatives. I'm not, that way I can keep it a little cleaner. Okay, so that didn't solve anything. Let's see what sum of forces in Y do for us. So in Y, we have 10 up, and we indicated that would be going down, so that would be AF vert is equal to 0. So therefore, AF vert, again, bring that over, that's positive, so you get a positive. So compression was correct. Compression was correct.
Okay.
All right, so now, again, we have to be careful because this number is 6.67 horizontally over 10, 6.6 vertically over 10 horizontally. So we can write that proportion. We can say that AF horizontal is to 10 feet as 10 kips is to a vertical distance of 6.67. So remember, this was 6.67. Go back to your initial diagram and look at it. Okay?
Okay.
AFH. Let's see what we get there. So we get 100 divided by 6.67. Basically 15.
Yeah, that's what I got.
Okay. Again, remember, there's a little bit of rounding going to be kicking around in here. Okay. So when we plug the 15 up in here, it'll solve AB. So that'll be 36 minus 15, which gets us what? 21?
Mhm.
And it was positive. So what does that tell us? We indicated compression initially. This indicate that says, yeah, you were right. So we were right in both cases. That's a compression member at 21 kips, and AFH itself is going to be 10 squared plus 15 squared square root. So AF, let's see, 15 squared plus 10 squared square root. You get 18.
Yeah.
18 compression, correct?
Mhm.
Okay. So there's two joints. I'll say now, if we go to B, we probably don't have enough to solve that. And we definitely don't have anything at E, F, or C. So your suggestion of going to D is probably a good suggestion at this point. You agree?
Yeah.
Okay, so, well, I tell you what, I take that back. At F, you probably do have enough information now because we solved GF and we solved AF. Okay, so we probably could go to F. But again, I think you want to use your D suggestion.
Sure.
Was that yes? I'm sorry.
Yeah.
Okay, all right, so I'm gonna clean my screen up, and then you guys may have to help me with these, okay? So I'm gonna go to D. So let me go to D, draw what's going on at D. D's really interesting. Watch what'll happen here. Maybe you've already figured it out, but I've got, oops, let me undo that. I want to be able to try to get two joints in here. So I got that member. And I got that member. And that's it. Nothing else is happening here, right? So what do we think's going on here with the directions of these members? We got DC. What do we think about DC? Compression or tension? Just make a call.
I'm just gonna go with tension.
Okay, we're gonna call it tension. Now this is a CD or DC. And I'm just gonna call this tension, okay?
Okay.
Because really, watch what'll happen here. Sum of forces in the X have to equal 0. So we got negative DC, right? Minus DE horizontal have to be equal to 0. Well, what does that say? In order for these to be 0, they have to be equal to each other, right?
Yeah.
Okay. But we don't know what anything's going on here, so let's try this. Summation of forces in the Y have to equal 0. So what's going on in the Y? We've got ED vert. What about it? There's no other forces, right?
Right.
So therefore, it has to be equal to what?
0.
And therefore, ED horizontal has to be equal to 0, right?
Yeah.
If that's 0, that's 0. So DC is 0. ED is 0. Think about that. There's nothing happening out here. So technically that says we could just cut that off of that truss and it doesn't do anything, right?
Right.
So that should make sense, correct?
Mm-hmm.
Okay, so good. Now that's good information. So now which joint would you go to?
E.
E would be too many unknowns, I'm pretty sure. But what about C?
Wait, is E on the top or is it? Oh, C. Okay. Yeah.
E's on the top, right?
Mhm.
Yeah, so you would have 1, 2, 3 unknowns coming into E, and the two of those are diagonal. So that would be really tough, probably a tough one to solve. But if you look at C, you could probably tell me by inspection what's going on there. What do you think about C? If CD is a 0, what's that say about CB? Well, let's draw it. Let's draw it. I'm going to go joint C. Okay, I'm going to start out here. Okay, I got to force this or a member this way and a member that way, right?
Mm-hmm.
And I've got what? A member this way and an external load. So my external load here is 14 kips. Agreed?
Yeah.
What happened with CD? CD is what? 0, right?
Mhm.
Okay. All right, so we got an unknown CE. What can we say about CE? Compression or tension?
CD.
CE.
CE.
Yeah, the vertical member here. Do you think it's compression or tension?
Let's say tension.
Yeah, look at this guy. He's pulling down. He better
Mhm.
pull up, right? If you want equilibrium. So we're going to call that CE. What about this guy? CB.
Tension.
Okay. BC, CB. All right, so sum of forces in X have to equal 0. Oops, X. All right, so we've got what? Negative CB,
Mm-hmm.
and that's 0. Has to equal 0. So what's CB?
0.
It's 0. All right, so sum of forces in Y have to equal 0. So we've got what? Minus 14 plus CE has to equal 0. CE, bring that over, comes over as a
14.
positive 14. So what does that tell you about that one now? Tells you that it's what? You indicated it as tension. So that's actually tension, isn't it?
Yeah.
Okay, cool. All right, so now we've got joint G and A solved and D and C. So
We need B and F.
B, F, and E, we need all
And E.
3. Okay. So let's look at B. We know what's happening at B because we know BC member, we know we've got an external load, and we also know AB. Is that correct?
Yeah.
So we should probably, we only have 2 unknowns there. We should probably be able to solve B. Do you agree?
Mhm.
Buddy? Do you want to go to B then?
Yeah.
Okay, I'm going to probably need help. You guys are going to have to tell me what's going on there. Let me go ahead and go and clean this up. And I'm going to do it joint. We're going to do joint B this time. This is joint B. And see if we have enough information to solve this guy. Okay, so we do have, we're going to have a vertical member unknown. Oh, we got another force there too, don't we? We have an external load there as well. So there's my joint actually. Now we solved that one and we've solved this one. And then we also have, let's see, we have a diagonal in here. Trying to get this drawn correctly. Okay, that's about 18 degrees. Okay. So here's my diagonal. Okay. Okay, what did this guy right here, this is member BC. What did we resolve BC to be? Wasn't that 0?
Mhm.
Okay. We have an external load here of 8 kips, right?
Right.
What did we solve AB to be? We solved that as a compression member, wasn't it? Did AB turn out to be compression?
Yeah.
Okay, so that means that he's coming in on the joint like this, right? The joint's compression. And that was 21 kips, right? Is that
Yeah.
correct? Okay. All right, so now what do we think's going on then with the diagonal component, BE here? This guy plus this guy, well, that's 0. So this guy's going to have to counteract the forces going this way. So compression or tension?
Compression.
Compression. Good. So if this guy's acting down and that guy's acting down, what does that tell us about BF? That's down, that's down,
So then it's got to be up.
that's got to be up, right? So again, you know, if you think, if you take a few minutes to do that, you can get these signs pretty much correct, and then you don't have the negatives. But, you know, if you don't see that again, and I've said that before, don't worry about it. Just don't worry about it, okay? So let's do our resolution. Sum of forces in the X have to equal 0. So in the X, we have 21 kips minus B, E, horizontal, right?
Mhm.
And the zero is out. We don't need to worry about that. That's equal to 0. So that gives me BE horizontal comes over as a negative 21. Negatives on both sides tell you that we definitely indicated that correctly. So we know that we are compression. Agree?
Yeah.
So sum of forces in the Y we have -8, that's my external load, plus BF minus B evert. And all of that has to be equal to 0. It gives me BF minus B evert is equal to 8. So this should resolve then. We can get the geometric relationship on this one. This has a distance of 3.33 in the vertical over a run of 10. So we know the horizontal is to 10, so we can say that BE vert is to the distance over which it's acting, which we said was 3.33 when we solved that earlier, as 21. The horizontal is to 10. So BE vert, okay, will be 3.33 times 21 divided by 10. Basically 7. Is that what you guys get? Seven. We're right on it?
Yeah.
Yeah,
Okay.
that's what I got.
Okay, perfect. And it was positive, right? Positive? It has
Yeah.
to be, right? If this is positive, that has to be positive. Okay. There's no way that that could be anything other than that. So that solves this guy, right? What does that tell us about BF now?
Yeah.
What do we get? Plug a 7 in here. -7 comes over as a +7, so that tells us BF is 15. We indicated tension. It's a positive number, so this tells me, yeah, your tension. And BE is 21 squared plus 7 squared square root. What do we get? 21 squared plus 7 squared square root. 22 basically. If you carry it out, it's like 22.1. And that would be a compression member. Do we agree?
One sec.
Sure.
Yeah, we're good.
It's okay that you guys are calculating numbers. That's great. But what's more important is make sure that you're following what I'm doing in terms of when I'm setting up my sum of forces in X and Y's and my relations. Okay. I mean, I want you to understand both, but really we need to look at that too. So I think you guys are following it. I hope you are, right? We're not going too fast, are we? We okay?
Yeah, we're good.
Okay. Okay. It doesn't sound real confident there, Max.
I'm a little tired. Sorry.
All right. That's all right. It's all right. I am too. All right. So we've got joint G, A, B, C, D. So we need to solve F and E. So what do you think is a good one to attack?
I'd go with probably F first.
Yeah, to be honest with you, I think we have enough to do either one of them at this point. So since you mentioned F, we'll go ahead and do F. And then the last joint we're going to do is E. And everything at that point should resolve to 0 if we've done this correctly. Okay?
All right.
So I'm going to go ahead and we're going to call that the member let's see. I'm gonna go ahead and I think that's like 18 degrees. I'm trying to draw this representative. This little tool is kind of cool because I can put what angle I want right on it. So I like that. All right, so I've got one going this way, one going this way. So this kind of looks nasty at first, but you're going to see this actually shouldn't be that bad. But we do have to reference certain things here, okay? So we have, okay. So I'm going to start with the vertical component. BF, we just solved BF to be a tension member, is that correct? Tension?
Mhm.
So this guy is going to be acting like this, 15. Now I have to go back and look. We had modeled, let's see, this member right here, that's GF. We had calculated that as a tension member, I believe, right? Was that tension? GF, didn't we solve that as tension? You have to go back and look on your earlier sheets. Anybody help me out? Was that tension?
Yeah.
Okay, so that's a tension member. So now what's more important with that tension is the fact that it has two components. So you're going to have a component acting this way and a component acting this way. So we need to solve or find those two values. Let's see, I'm going to move my symbol for F out of the way. Getting kind of cluttered here. Whoops, I drew that wrong, didn't I? Anybody see my mistake? This guy can't be going down, has to be doing what?
Up.
Up, yeah. And you know what? That's an easy thing to do, by the way. So, you know, watch that because, you know, you can do that real easily. So this actually is an up member or up component. Let's get this out of here. I was wrong. Okay. So what were the two component values for the horizontal and vertical of GF? Anybody find those? The total value of GF was like 37.9, I think.
Yeah.
I had a vertical component of GF. Was that 12?
20 for G.
For GFV. Yeah, this member right here is GF.
Yeah, it was 12.
Okay. I'm going to put this. This is GF. So what was the horizontal component of GF?
36.
36. Okay. So remember, if this guy's going this way, these guys have to go that way. So I had that mistake going down. That could have been a really bad mistake, by the way. That was something that really can happen. All right, so now we've got this member. This is member AF. And you have to, I think that was the second joint we did. AF turned out to be, what do we solve that as? Compression? Is that right?
AF.
Compression? That would have been the second joint we did. Go back and look that up.
Yeah, that's compression.
Okay, so that means this guy's coming in on us, right? Like that. So again, we're going to have two components associated with this. One going up, and the other one is going to be going this way. So we've got this guy and we've got that guy. Okay, so the horizontal component was 15, if I'm right. And the vertical component on that guy was what? 10. I think that was 10. You guys agree? So this was AF compression,
Yeah, it's 10.
10 and 15. Okay.
Mhm.
All right, so as we look at this diagonal, which only has that's the only unknowns, what can we say about it? You notice that the 36 and the 15 are out of balance, right?
Yeah.
So this guy has to do what? Pull or push?
Pull.
All right, so he's tension, right?
Mhm.
Now, if that's true, if that guy's going that way, this has to go down, but notice we've got 10 plus 12 is 22 and 15. So yeah, that makes sense, doesn't it?
Mhm.
Okay, so we're going to call this FE. And let's see what's going on here. Sum of forces in X have to equal 0. So in X, we've got what? Minus 36 plus 15. That's this 15 here. Plus FE horizontal has to equal 0. So when we do the math on that, 36, okay, I get a negative 21, comes over as a, I'm sorry, let's see, is that right? Oh, what did I do wrong here? Anybody see what I did wrong in my equation? I've got a mistake in here. Negative 36 is correct, right?
Yeah.
Positive 15 is correct, right?
Mhm.
Yeah.
What about this? This is not going negatively, it's going what?
Positive.
Positive.
So I made a mistake, okay? When I did my math, it didn't make sense to me, so that's why I caught that. Okay, so this, then that gets you a negative 21, right? So it comes over as a positive 21. Okay, is that good?
Yeah.
Okay, so you can see anybody can make mistakes, but you just have to think about it sometimes when you're doing this stuff, okay? Okay, so Y, we have in the Y, we have positive 12, positive 10, negative 15, minus, this one is minus, FEV has to equal 0. So we're going to get 10 plus 12 minus 15. That gives me 7. That's what I came up with. So I get a positive 7 comes over as a negative 7. So you have a negative on both sides. So you get 7 and 21. Is that good?
Mhm.
All right, so now, since we solved both of these components, we should compare them to the geometry, and we can see if we got the right answer here. So if we get the right answer, we're good. So horizontal, 21 kips is to 10 horizontally, as 7 kips is to 3.333. If that geometrically relationship doesn't work, then we got a problem. So I get 2.1 on the one side and 2.1 on the other. Okay, so this is correct. You guys agree with that?
Mhm.
Okay, so now we can solve FE. That's going to be 21 squared plus 7 squared. 21 squared plus 7 squared square root. Basically 22. And that's a tension member. All right,
Yeah.
we good?
Mhm.
Okay, we have one more joint to do. I'm going to go ahead and clean this one up here. You guys are, remember, let's see, BE is going to be feeding into me, so remember BE is compression, okay?
Okay.
All right, so I'm going to go ahead and take this out with a nice little deletion window. All right. What's that? All right, so we're going to be the last joint. Everything should resolve to 0 at this point. This is joint E. Going to start joint E here. Okay, so we've got, I'm going to probably move my, I did that wrong, but probably going to remove that E. So we got that going on. Let me move my E here. Okay, so this guy right here is CE. What did we solve CE to be? I think that was a tension member, wasn't it? CE was tension,
Yeah, it was.
and that would be going this way if it's in tension. Do you have the magnitude of that
32.
for CE?
Uh, yeah.
I think it was 14.
Oh, I could be wrong. Let me look.
Yeah, look at that.
Oh yeah, I'm looking at the wrong paper.
That's fine. That's fine. Got to make sure, right? Got to make sure.
Yeah.
That's the biggest thing about this. You got to really watch.
Yeah,
it.
it's tension in 14.
Okay, so the tension was good. We just had the wrong value. What about ED? Wasn't that 0?
Yeah, ED was 0.
All right, so that's 0. Now we just solved this guy. This was FE. FE is a tension member, correct? So he's like this. That's FE. And so we've got two components on FE. We got one going this way. And one going this way, correct? I got those right this time. So if we look over here, vertical is 7. And the horizontal was 21, right? So the only other member we need here, and I said you guys would have to help me with because I don't have it on this picture, is BE. So BE, I think we resolved as compression.
Yeah.
Let's verify that. Is that right?
Yeah.
Okay, so we need the components of that compression. So I'm going to have one going horizontally and one going vertically. Like that. So we got this guy and this guy. What were the components of that? They better be 21 and 7. Yeah, it looks like I got horizontal for 20, 21 and 7. You guys agree with that?
Yes.
Okay, so everything should resolve to 0, right? Sum of forces in X have to equal 0. So in X we have minus 21 plus 21 definitely equals 0. So that checks. Sum of forces in the Y. We have 7 up and another 7. So 7 plus 7 minus 14. That definitely resolves to 0. And there's your solution. little bit long-winded problem. Got a lot of good geometry in it. You really just got to keep track of what's going on. Okay, so there's your solution. Questions?
No?
Feel better about it, Max?
Yeah.
The one thing you had to deal with was a similar triangle distances, so you got to come up with a distance that's really helpful. Those were simple enough to get. There's a lot going on here, so all of these problems have a lot going on. It's like I've said before, statics is a lot of bookkeeping, and the more you recognize that, the easier it becomes. Okay.
Okay.
All right, so unless you guys have another question, and we're getting out of time anyway, but anybody have anything they want to discuss about this or the test, or you ready?
Pretty much good.
Good. All right, so look through all of those problems, okay? So I gave you problems, the first section, and then I gave you some more problems they're listed on Blackboard for your homework problems, but for the sections, you should be able to do problem 10 through 17, okay? And,
Okay.
I will be here tomorrow, just, waiting for questions. I think I do have an appointment at 11 or 10:30, but other than that, you guys can email me, or I can do a Zoom session with anybody from 8 o'clock until 1 o'clock. And then we'll take a look at a problem or two before. I just want to make sure you have 2 hours at least to solve that test, okay? So that'll give you an hour for each problem. And you're going to have 2 problems. One problem will be a joint. One problem will be a section. You won't have a choice on which to do. I'll tell you, you got to do one this way and one another way. Okay. So, anybody else?
Nope.
Okay, perfect. Well, I'm going to go ahead and stop the recording. And I will go ahead